The current density J at a point within a conductor where the electric field is E is given by E equals rho times J. Here. It's often difficult to measure E and J directly, so it's useful to state this relation in a form involving readily measured quantities, such as the total current and potential difference. To do this, consider a conductor with uniform cross-sectional area A and length L as shown. So here we have a conductor with cross-section A and length L. Assuming a constant current density over a cross-section and a uniform electric field along the length of the conductor, the total current I is given by I equals J times A. So the total current here is I equals J times A, marked as equation 3. And the potential difference, V, between the ends of the conductor is V equals E times L. So here we have the potential difference, V, between the ends of the conductor is V times the field times the distance. In other words, the field times the distance, L. So we have the potential difference of V equals E times L, which is marked as equation 4. Solving these equations for J and E respectively and substituting the results into equation 1, into this equation up here, we obtain V over I equals rho times L over A. Thus the total current is proportional to the potential difference. So we can normally write down R equals rho times length over A. So equation 5, this equation here, becomes V equals I times R, equation 7. So this then becomes this equation. This equation relation is also called Ohm's law. In this form it refers to a specific piece of material, not a general property of the material as with equation 1. So Ohm's law as a general property of the material, and this is the more common one we're familiar with, V equals I times R. Also, this equation here shows that the resistance of a wire or other conductor of uniform cross-section is directly proportional to its length and inversely proportional to its area. It is, of course, also proportional to the resistivity of the material which the conductor is made. So we can work out resistances of materials just by these three variables. Because the resistance of any sample of material is proportional to its resistivity, which varies with temperature, resistance also then varies with temperature. For temperature ranges that are not too great, this variation may be represented approximately as a linear relation as follows. RT is R0 1 minus alpha T minus T0. Here RT is the resistance of temperature T and R0 is the resistance at temperature T0. So T is the temperature, is the final temperature, T is the initial temperature, and RO is the initial resistance. T0 is often taken to be 20 degrees C or 0 degrees C.